This video is the mechanism of the acetoacetic ester synthesis. So we're starting with the ethyl ester of acetoacetic acid, and the reaction is carried out in the presence of ethoxide and the solvent is ethanol. We do that to make sure that the esters don't transesterify. I've also highlighted the hydrogen that's on the carbon that's alpha to both of the carbonyls. So the first step of the mechanism is deprotonation to give us this highly stabilized enolate that's alpha to both the ketone and the ester. Because there are two carbonyls here, this deprotonation happens to completion. Now the enolate is reacted with an alkyl halide. I've chosen a propyl bromide. Primary alkyl halides are important to use to avoid elimination side reactions. So we have an SN2 reaction that happens when the enolate attacks the carbon that has the bromine leaving group. And that gives us this alkylated acetoacetic ester. There's one more acidic hydrogen, so we can deprotonate at that position and give us another enolate and alkylate it a second time. I chose to use the same alkyl halide because I wanted to put two matching groups on there. So here is my alkylated product, and then again this is an SN2 reaction. I'm going to hydrolyze my acetoacetic ester with sodium hydroxide and water, and I am choosing not to show the mechanism for those steps here. If you want to see the mechanism for ester hydrolysis, go look at the ester hydrolysis reactions. This was in base. So I get the carboxylate anion and no decarboxylation happened. That only happens in acid if there's heat around. So the final step is neutralization of this carboxylate with acid. That's done quickly under cool conditions, so decarboxylation doesn't happen there. And if you wanted to decarboxylate, you should do the hydrolysis in a different way.